Yeah, all right. Hi. My name is Lukas. I'm a PhD student at Akademi, and today I'm presenting like a chapter that potentially goes into my thesis. It's called The Influence of Hydrodynamics and Habitat Complexity on Eelgrass Seed Trapping, which I have conducted together with my supervisor Christopher Boström from Akademi and Eduardo Infantes from the University of Gothenburg. Yeah, as you know, Zostera marina relies on both vegetative and sexual propagation, and the sexual propagation is particularly important for demographic and genetic connectivity. And dispersal distances of seeds can reach between a few meters when the seeds are traveled or transported as bed loads via currents or waves, up to several kilometers when they're transported as floating or via floating reproductive shoots or biotic transports through the guts of vertebrate and vertebrate species such as fish and birds, for example. However, the mechanisms for the trapping of eelgrass seeds is to date quite poorly understood. There's only like a handful of studies that actually address this topic. And we tried in this study to quantify seed trapping in different biogenic habitats, eelgrass itself, but then also we wanted to see whether bivalves such as blue mussels and Pacific oysters actually are capable of trapping eelgrass seeds compared to bare sand habitats, for instance. So we did like a flume study using Eduardo's flume in Kristineberg Marine Station in Gothenburg. And just to get like an idea of our experimental setup, we had like a test section of about 60 to 40 centimeters within this flume, and we planted these different habitats we had. And then released seeds in front of the test section and just basically noted how many of them were retained within the test section. So in total we had 16 different treatments, of which we had 3 treatments for smaller eelgrass shoots up to 15 centimeters, 4 treatments for quite large shoots up to 30 centimeters. We had 3 treatments for oysters, so 3 densities of oysters, and 1 density for the blue mussel. And additionally, we had 5 treatments where we tried to intermix between eelgrass and bivalves to see if there's like an additive effect of different structures for eelgrass seed trapping. And for each of these treatments, we applied 10 different current velocities, ranging from 12 to 30 centimeters per second, to get like a bit an idea of how hydrodynamics actually affect seed trapping. And we were measuring, as I said, the trapping. So we released 30 seeds and measured how many seeds were retained within the test section. But we also took ADV profiles to get a bit an idea of how flow and turbulence changes before or after the test section, to see if that had an effect on the seeds as well. And then we also measured sediment scouring, so erosion of sediment behind different objects, by putting a camera in top view position and taking a picture after each trial, and then just using ImageJ to basically calculate the area of sediment erosion. This is just maybe a quick video that works of how this looks. I wasn't aware of the music, I'm sorry. You can see the seeds. For example, this one just got trapped here, but a couple of them just passed through the whole test section. Oh, sorry, but I'm actually done. It's fine. Just, it's really short. So, sorry for this. Anyway, just to show some results, so we had 160 trials, and this is the results for our small eelgrass shoot treatments. So you can see this is the trapping success, and this is the flow velocities reaching from 12 to 30 centimeters. And you can see that for the different densities, we actually get quite different results, showing there's a huge density effect. So the more seeds we put in, actually the higher the trapping, of course. The more shoots we put in, the more trapping we get. But you can also see that flow had a huge effect and a different effect on each of this density treatments on seed retaining. So for the lowest shoot density, almost none of the seeds got stuck within the test section, independently of the flow velocity. For the intermediate shoot density, you can see quite a lot of trapping, up to like 30% under low flow, but it decreases quite a lot when we get higher flow or applied higher flow. For the high shoot density treatment, we got quite a lot of trapping in the beginning, and then we got this decrease again. But surprisingly, we got a huge increase suddenly when we reached like really high flow velocities, and this was due to sediment scouring, so sediment erosion and movement of sediment behind each of the structures, and they were actually able, this little pits, to trap the seeds quite effectively. And we got similar results for large shoots as well, so we got this initial decrease quite often, and then towards higher flow velocities we got huge amount of trapping up to almost 100%. And you can see that for large shoots we get like quite a lot of this scouring, and I will show a picture later how this actually looks. But yeah, and what we also could find out is that bivalves were quite capable of trapping this different eelgrass seeds as well. And again, here you get a huge trapping success with high flow velocities, which was quite surprising for us at first. And to just get an idea of how this looks, when you apply like high flow on biogenic structures within the flume, you get this huge scouring patterns here, and in here you can, for example, see how one of the seeds is trapped. And the same for the oysters, where the seeds just stuck behind these patterns. And when you just look on these graphs, where you can see the percentage of seeds that were trapped, or the location of seeds where they were trapped. So you can see that under low flow, most of them were just trapped like either in front of a shoot or behind a shoot, or in front of a bivalve or behind a bivalve. But the more flow you get, the more important this scouring became, and it reaches up to 7% at really high flow, and for the bivalves even way earlier. You can see this pattern. So to just quickly sum up a bit our results, we could show with all this data we had that habitat complexity and flow velocity both had quite a significant effect on seed trapping, and flow velocity had mostly like a negative effect when this scouring patterns didn't appear. But as soon as scouring patterns were big enough, you could actually see that flow had quite a positive effect on seed trapping, together with habitat complexity. And when you sort of sum this up, then you get, and you see that habitat, or that there's a density dependent effect on seed trapping, then you can think about a positive feedback that the more seeds you actually get, the more seeds you can trap, the more shoots you get, and the more shoots you have, the more seeds you can trap. And this might be sort of one mechanism for patch emergence as well. But on the other way, you see also that this is a bit dependent on density, or initial density, or threshold density, because when you have like almost no shoots there, then trapping is, trapping is just, 3, 4, 5%, and it's probably negligible. So to conclude from this study, that we could show that both shoots and bivalves were quite effective in trapping seeds compared to bare sand habitats. And we also could think of this density dependent seed trapping, that what I just mentioned, that the more seeds you get, the more shoots you get, the more seeds actually get in there, and this could potentially be one of these positive feedbacks. However, I know, of course, clonal propagation is probably more important when it comes to patch emergence or patch growth, but this could be one additive effect. And there's a couple of studies on sediment scouring that have actually associated the scouring processes with negative effects on seedlings, because they got uncovered and at some point washed away. But we could quite clearly show that this at least facilitates propagule trapping. But also, due to this erosion processes, the seeds actually get buried within the sediment. And there's a few studies suggesting that burying or seed burial is quite beneficial for seedling development, because it reduces predation, but it also increases germination success and makes sure the seeds don't get washed away. However, if they get buried too much, I think more than 5 centimeters might be harmful as well. So this is not just a positive effect, but at least it certainly could be. Yeah, and I think that's it. Thanks.
Well, thank you, Lukas, for your very clear presentation. Are there any questions?
Just a short one. We have been out in the field and we are absolutely, without saying, we are full of scouring mechanisms out there, and we find 0 seeds inside very dense patches, including whatever, of other structures, saying, and I think it's due to that we out there have a full 3-dimensional patterns of stress from the hydrodynamics. To me it seems like it is a unidirectional setup you have, and you even don't have a setup where you are simulating tide. So the scouring you are getting here, it don't include wave actions or the tidal. So I think you should be a little self-critical about results like these.
Yes, of course. I mean, the applying waves was one idea of. I mean, we were running out of time when we applied this experiment, and it was the easiest because I've never worked with a flume before, so it was the easiest just to apply currents in the beginning. But the idea is to actually go back and actually see what happens with waves. But then on the other hand, wave is quite difficult in a flume because, I mean, you get this oscillating movement, and seeds might not really actually move within the test section unless you apply a bit of current, and I'm not really sure how to deal with this to get both in waves and current at the same time. If that's
So just as an example, in our flumes we have the options, but it's still not the final image we have, but we have the options for programming it, so we have the current simulating actually the tide, so the current direction is changing as a tidal pattern, but we also don't have wave included in the physics.
Any other questions?
So it strikes me you can actually measure the actual shear on the seeds associated with each of these different structures. Have you tried the bed shear calculations on the seeds? Yeah, it might be interesting to just find out how much force they've had. Yeah.
When do you mean when they start moving, or when?
Start moving.
Yeah, I mean we just basically used free flow to see when they start moving because it was a bit easier to work with the ADV to handle this. But I think initial movement for seeds just to start moving within like a really plain sediment, it was about 10 centimeters per second.
I was thinking more that if you can give us those numbers, I can use them in a model.
All right, you can have them.
One more question? Okay, so let's move on to the next speaker.